Okay, so I started recording. I'll be posting this video later again, like all my other stuff. But I may post some videos too on the homework, just because the homework's difficult. And let's see if I can share my screen. Okay. So let's just hop right into it. Today's lecture is the 5th lecture, and it's on Chapter 2, sections 7 through 9, which is moments about a point in 3D and moments about an axis in 3D. Point and axis and 3D. So we get to do more of what we have been doing, but putting it in a 3-dimensional field, which is a little bit complicated if you're not familiar with working in 3D, but all of the concepts are the same.
Excuse me.
Yeah.
What is that word after about? Is that
It's 2 words that I left out all of the vowels for some reason.
okay? Thank you.
Vowels in that word. Yep. That helped. I'm glad that y'all showed up to help me fix all those little confusion things. So in 3 dimensions, you'll have an x-axis, a y-axis, and a z-axis. That can also be I, J, and K. And if we were to have a, say, a force vector that was in these 3 dimensions, we can organize it and define it by angles from the respective axis. So this would be a theta x, and the angle between that force vector and the y-axis would be theta y. And as you can probably imagine, this is going to be theta z. So you can define it in that way. Typically, we don't define it. We define it in a different way in terms of planes rather than these individual angles. But one of the first or second homework problem asks for the angle in between. So I want to make sure that you're aware that it can be defined in this way. And to solve for those, the force along the x-axis, which is going to be that distance, is equal to the magnitude of this force times cosine theta x. And in the same way, f of y equals f cosine theta y. F of z equals f cosine theta of z. And mathematically, this is the simplest way to define these, but unfortunately, we don't usually have this kind of information. Typically, and what you've probably seen before and will recognize, is organizing the coordinate system in terms of the projection of this force onto the plane. With this angle being phi and this angle being theta. So you have your original force, then you have a force that's on the plane XY, and then you can identify it in its components. So these are two different ways to identify a vector in 3D. And the reason this way is more common is because we're used to working in vectors and planes. So what we've been doing before has all been the force in the XY plane. Now all you're doing is adding a third component, which is a next step beyond what we've already done. Whereas here, we've never looked at these angles at all before because we're so used to looking at angles that are in that 2D plane. Both are helpful, they have their place, but this is going to be probably more comfortable. Oh, let's see. So this is the way that's more comfortable. Let's now solve for f of z, f of x, and f of y. F of z is kind of its own angle because it's directly related to that z-axis. But as you can probably imagine by the name of this force vector here, these are both related to f of xy, which is this force in the plane xy. And f of xy equals the force cosine of phi. So this angle on the cosine side, fairly straightforward. But now you have to go more steps to actually find f of x and f of y by using that theta. So we're going to continue using f of xy, but now for the f of x, we'll use cosine of theta. F of y will be f of x, y times sine of theta. Now you can convert these by plugging f of xy in, and you get f cosine of phi cosine of theta, f cosine of phi times sine of theta. And these two parts are the same because it is just the force in the xy plane. Now we have f of x and f of y, but we still need f of z.
Should that sign at the last thing, is that phi or theta?
Theta, you're right. Thanks.
Okay.
F of z is going to be phi though, because we're looking for this vertical here, and that will be f sine of phi. So you can see that the z is the easiest to get because it's only one step. You don't have to do two different angles, but it's also the most difficult because we are so used to working in the sine theta, cosine theta field. Now we're adding on this third dimension. Is everybody following along with that? Now, I was talking with a student the other day, and they had a great point about knowing how to tell the x, y, and z in the coordinate system, because you draw this, but what do you put where? How do you keep track of x, y, and z's? Because if you were to put x here, y here, and z here, you would find that this was actually a negative z in terms of the right-hand rule. And when you're dealing with moments, you need to be able to keep track of the signs in 3 dimensions. And she gave me a great trick. So let's see. If you take x cross with y, you get z. And this is as if you're going to the right. And y crossed with z, you get a positive x. Z crossed with x, you get a positive y, and that's as if you were to continue this going. So this crossed with this is positive z, y crossed with z is a positive x, z crossed with x is a positive y. If you were to find yourself going the other way, then you would get negative values because it would be this situation here. And in this case, z crossed with y is a negative x, y crossed with x is a negative z, x crossed with z is a negative y. So that is a little trick that you can use to follow the signs, or you can just memorize it conceptually. Little tricks are always very helpful to me, so do that with what you will, but XYZ. But typically what we'll see here is X, Y, and Z. X crossed with Y equals a positive Z. Now let's get into some moments in 3D. You just had a crash course in regular 3 dimensions. And as we've talked before, R cross F is the moment. We've been doing primarily in 2 dimensions, which is nice because all you have to do is look for perpendicular vectors. But in 3 dimensions, it's really complicated to do that. So I would suggest just always using R cross F. You can always use the calculator online with Wolfram Alpha that I showed you last time, or do it by hand. I'm going to write down the equation in a second for all of the, it will cross out through as if they're values in every one, where we've been having 0 in the z direction in our original vectors. X hat, y, and z. Say we have a force here, and this force has x, y, and z components, so it is a 3-dimensional force. And we had some kind of beam here, and this beam also has 3 dimensions. And you can identify this beam using that same method that we had before, where you put phi here and theta on the ground. And let's say that we are given the unit vector for this force. So we know each of the components in x, y, and z. That's something that's given to us. If we were to look for the moment about O, that would automatically make this our R vector. Say this is point A, and that would be A with respect to O. And this is a force of x, y, z. If we were to do this the longhand, you would take the determinant of the unit vector I, j, and k, and you would put Rx, Ry, Rz with f of x, f of y, f of z. If you want to use the trick, if you go down and to the right and multiply across that way, it's going to be positive. So for I, it would be R, positive R of y times positive R of z. If you go negative, you'll take a negative k times R of y times f of x. But you can also pretend that you've already done that and just include all of the values. So multiplying all the way out, that is Ry f of z minus Rz f of y in the x hat direction. So that's taking I, multiplying it down, and then going to the left using f of z, r of z, and f of y. And you can do the same thing for the y. R of z times f of x minus r of x times f of z, y hat. And the same thing for z, r of x, f of y minus r of y times f of x. So that'll be a little bit long equation. And in 2 dimensions, you will only have this. So if you want, you can just memorize that because it never changes. I will be providing this on the exam. So this will be part of an equation sheet that I provide. So if you don't want to do this rule or even plug it into your calculator, just know that I will have this full equation on the equation sheet for moments in 3D. And when we take this moment, let's see, it's going to be negative because right-hand rule. So we can either write a negative moment this way, or we can have going into the back of the page having a positive moment. Because it's making our page messy, I'm going to bring the negative moment over here. But this will take into account all of the signs. So if it does tell you a negative moment, you know that right-hand rule is going to be going that way. Science will tell you everything about it in this way, and that's why it's kind of nice. In a second, we're going to do moments about an axis, and following the signs is a little bit more conceptual, and it's not quite as nice. So just be happy that the signs are taken care of for you here. So if you had, say, a door, and you had the hinges on the wall, and for some reason there was a lot of gunk in the hinges, or they just weren't working very well, they were kind of bent, and they're applying their own kind of torque here, you need to know how hard to push on the door to make it close. But you don't really care about the moment of a certain point. If for some reason, say the doorknob is really high and you're pretty short and you're pushing up on it, you don't care about the moment that is pushing upward on the door. You only care about the moment that is going around those hinges. Well, you can calculate just for the moment going around those hinges rather than the entire moment of the door, say at some point in the middle. And that's really helpful. And the classic example is hinges, but there are other times where you'll want to find the moment around an axis as well. And we, once again, have a force here. That was not. This time our force is in 2 dimensions, actually. So this force is in the x and y, and it is defined by theta. And we have a beam that is vertical here. With a positive axis going this way. R is just in the z direction. So if we were to cross R, that it has a z component with F that has an x and a y component, you would get a moment that has an x and a y component. And right-hand rule, that moment is going to be positive. So you can find it here. This moment is just in the x and the y. But how do we define this moment in space? Great, we use that equation that we had before. But what about if we were looking for this moment along this a-axis? Conceptually, we have that in the area. Practically, I have no idea what this a-axis would be, but let's just take a look at it and see how we would find that. The easiest way would be to define this angle as phi. And you would take the moment about O along the a-axis, and you would take the magnitude of the moment about O times cosine phi. And because it is going in the negative direction of this axis, you would have a negative sign in front of that. And that is the easiest way to get the moment along the axis. You're just looking for the component. Say, think of A as a new reference frame. Unfortunately, just like we found in the first example of looking in 3D, we don't often have that angle that's in between the moment vector and this axis. We don't often have that. So unfortunately, we can't use this very often. So the steps are going to be a little bit longer and a little bit more complicated, but it is easier than finding this angle here. If you're given the angle, use that. So first thing is we have to mathematically calculate that moment, which we've looked at it conceptually up there, but we need to actually calculate it. And the moment about O, and that is going to be a vector, is r of z cross x of y, which is great. Then we can calculate this magnitude here by doing a dot product. And you actually do dot product a lot, you just don't really think about it, because this here is a partial dot product of that moment. I don't want to get too into detail, but you're actually more familiar with this than you realize. That was all you need to know for that. So if I was to take the moment, and this is going to be a scalar, of O along A, we're looking for the magnitude here. You'll take the unit vector of A, which let's say that's given to us in terms of X, Y, and Z, and you dot that with the moment that you're given here. You're then given a scalar, and don't forget that scalar has no direction. However, we do know a little bit of what's going on with the scalar because we know that it is in the negative-ish direction. And I say ish because we don't really know the direction since it's a scalar, but conceptually, our moment vector is going towards the negative rather than the positive. So mathematically, it's going to come up with a positive value as a magnitude and absolute value, but in our mind, we know that it's going away from the positive axis. And because it's a scalar, even though we know it's the projection onto this, it really could go in a circle because it doesn't have direction. It can be pointing anywhere. So now we need to define that scalar as going along the axis. And how you do that is by multiplying the MOA, because we need a vector, MOA times n of a, and it's going to be negative because we know it's pointing in the negative direction. Earlier when I said finding a moment in 3D space is nice because the signs are all taken care of for you, the cross product tells you exactly which direction it's going. But about an axis, because we have to convert it into a scalar component, it rips away all of our directions, so we have to conceptually remember if our moment is going positive or negative, and it's a little bit more thinking, which is unfortunate. I always like problems that once you get into, they kind of work out for you. So we get a lot of equations now because we just did a lot of different steps, and each step individually makes sense, but you have to track where you're going, and you also have to know where to go when you start. So let's go back to the very, very, very beginning. Looking for the moment around O, that is R cross F. Then we look for the scalar or magnitude of O along the a-axis, and that is going to be the moment of O, A dotted with N of A. That can also be written as R cross F dotted with N of A. Then the next thing that we're looking for is the component of that moment that's along the x-axis in the direction that is required. And that is MO of A, and the magnitude times negative N of A. Also, you could write that as the vector moment about O dotted with N of A times negative N of A. If you wanted to do more substitution, that is R cross F dotted with N of A times negative N of A. And if you were working this as a problem where you had to find R, you had to actually find the unit vector, so that would probably be R over the magnitude of some R. Sometimes there's some more steps in getting that information, but we're going to see that in the example problem in a few minutes. So be sure that you know how to track this down in all the ways. Think about it in the little steps because that's where it makes sense, but also just don't forget generally where you're going. You're going from a vector to a scalar back to a vector. Okay. I am running out of time for my personal account Zoom links. So I'm going to end this recording now, and I'll send out another link that you can join in because it's going to cut off in a second. So I'll send out a link in a second.